to kick off the like basically what we're here for, the Circom 2.0 workshop with Iden3. So if Albert and Jose could join the stage, and actually Kobe and Susanna, you're free to go. We'll see you again at the end of the session. Hi, Jose.
Hi, everybody, nice to meet you.
Hi there.
Hello.
We have also here Jordi Bailina, who is the creator of the monster.
Oh, by the way, if you're hearing some echo, Jose or Albert, just make sure you close any other browsers that might be open. Sometimes people have, I just heard that a little bit. Yeah. That might actually help you out a little bit. Just make sure there's no other hop-in open if you're hearing any sort of feedback. But do you want to invite, is Jordi meant to come to the stage? Oh, you're muted.
Well, in fact, Jordi is on my side, so.
Oh, no way!
Yeah,
hey, Jordi.
He's here.
Hello, guys. Well, I just want to say just 30 seconds here and say that we are very excited right now because it's the first time that we introduce Circom 2.0. It has been a huge effort. I need to say thank you to a lot of people, starting from the Ethereum Foundation that got a grant for doing this, for rewriting all this in Rust. Of course, to the Universitat Complutense de Madrid with Albert in front, also Universitat Politécnica de Catalunya with Jose in front, all the people in Iden3, and especially all the Iden3 community in the chat that has been doing a lot of work there. So I hope that you enjoy. Right now, the Circom 2.0 is a step forward in what was starting like a toy at some point, and right now we just gave a step forward to do a professional and production ready and much tester, easier to auditable. Well, you will hear a lot about this by Albert, and then in the second part, Jose will do actually the workshop. We'll start from the scratch and create a circuit from the beginning. So I hope that you enjoy. Thank you all, and just enjoy the workshop. And thank you, Anna, for all your work there.
Cool. All right, well, I'm going to actually hand it off to Jose and Albert. I'm going to close my video. I know you have, as I understand it, Albert, you're going to start with a presentation, and then there's going to be more of a hands-on workshop. You guys should all know there's two chats. There's the event chat and the sessions chat. Focus more on the sessions chat for anything here. And there's also a Q&A. I don't know if Albert, if you guys want to check that out every once in a while, but we're going to be around to moderate so we can highlight it for you.
Great.
Perfect.
So should I start?
Yeah, I would do a screen share.
Okay.
And then Jose, and I'm going to drop off. Jose, you can stay on and maybe mute yourself in the meantime. And I think is it okay if people ask questions as you're going? That's the question in the chat. And actually, I think Jose, you were going to jump in.
And help answer them. It's okay if you ask questions as we go. So yeah, I will take a look.
1 second. I don't know if this is the way to go. Sharing. Oh.
Oh, all the things.
Is it this okay or?
We see it.
Yeah.
There you go.
Is it fine like this?
Looks great.
Oh, sorry. I'm a bit at the beginning. Not at the beginning. Sorry. Oh, there was
all the way. Okay.
A lot of. Okay. Sorry.
Okay. Good. Take it away. Here's the workshop.
So here we are. So I will start with the presentation. So you have already seen Jordi and Jose and myself, but I will start with the presentation. As Jordi said, this is part of this Iden3 project and funded by the Ethereum Foundation, and we at the university we are part of it as well. So this is gonna be the overview of docs. So I will do it really quick, this part, because I guess that most of you know what we are talking about, but just to give a little bit of context to later introduce the Circom language and compiler, and I will make a
I will give some time to describe the differences or what has changed from the previous version of Circom that needs to be known for those that were already working with Circom, and now they needed to change minor things to make them compatible with the new compiler. I will then conclude with a little bit talking about the constraint simplification, which is a really key part of the new compiler, and I will talk a little bit about performance. And then Jose will come and will give you a real practical tour using Circom 2.0. So let's start with this. So we all know that transparency is very important and desirable property of the distributed ledgers, but well, privacy is also that we want to guarantee in many cases. So we need to find this balance between both properties, and zero knowledge can be a good solution in this way. So what is a zero knowledge proof or protocol? It's just this protocol between these two parties in which the prover can convince the verifier that some statement is valid without revealing anything about the statement apart from the fact that it is valid. So we have this completeness, which is that honest prover can convince a verifier, soundness, that malicious prover cannot convince a verifier, and of course the zero knowledge part, which is that nothing will be shown beyond the validity of the statement. So the key point here to introduce why we use these languages in this context is what kind of statements can be proved. And then is when we come to arithmetic circuit satisfiability. So here, our statement is a deterministic arithmetic circuit in which we are given some public input, some private input, and we produce an output. So given a circuit and the inputs, the prover runs the circuit and generates a proof. Okay. Then, given the proof and the public input and the output, the verifier can check that the prover knows the private input and has executed the circuit. Okay. So, on the most important part, nothing is revealed apart from the fact that from the information about the private input, which is already known. So let's go a little bit on this circuit part and what's a circuit. And there's nothing more than a standard circuit, but where the gates, as you can see here, they're multiplications or additions. Okay, so every time we have such gates, so we get the result and so on. And this gave us this important thing, which is this quadratic constraints. Okay, you see here we have that this output here we call this met1. It's the result of the multiplication of these two. This met2 is the multiplication of these two, and the output is the sum. Okay, so these are quadratic constraints. But just keeping this in mind, so we need these quadratic constraints, and we don't want things that are not quadratic. For instance, if we express it directly like this is not a quadratic constraint, okay? Because here this is not quadratic, this one. Okay, so another important thing is this notion of simplification. Here you can realize that this intermediate signal is not really needed because we can express the output like this, and this is still a quadratic constraint. Okay, so here just a multiplication plus adding this this signal. Okay, so the important property is that the circuit operates on values in a finite field. Okay, where this P of the finite field is a large prime number like this. Okay, so somehow we work modulo this prime number all the time. Okay, and the important thing in our context is that the constraints describe the arithmetic circuit and are given in this R1CS format, which is a format of this form. We saw last week that there are many languages working with this format. There are other formats, but we will talk about this R1CS format, in which all constraints should be of this form, where A, B, and C are linear. Okay, see? So all should be expressed this way. Okay, and executing the circuit, which is something that the prover has to prove, it's done, it's obtaining a value for all signals in the circuit. And we call this the witness. Okay, so somehow we need these constraints in this format, and also we need this witness to show that we have executed the circuit. Okay, so just very quick, ZK snarks. Okay, so how do we generate this ZK proof and the verifier? And this by means of these snarks. Okay, in these snarks we have that they are not interactive, although we pay this the price of this trusted setup. It must be done properly. And what these snarks do, among other things, is to transform these R1CS constraints into these quadratic algebraic programs, arithmetic programs, sorry. And the key point is that these snarks generate short proofs, and they are implementations with constant time verification. In particular, Snark.js, which is another tool of Iden3, which combines very well with the Circom language. So let's go into the Circom language, and this is the picture we have shown. So we have this computation that we want to prove it's been done, but this computation must be stated as an arithmetic circuit. And then from this arithmetic circuit, we get this R1CS format for the constraints, and if we are given the input, we get the witness, okay, the values for all the signals. And all this is sent to Snark.js, and we get the prover and the verifier. And in fact, we get the proof and the verifier that can check the proof. And in particular, this verifier can be given as a Solidity code as well. Okay, so here we have that the Circom language help us here. Okay, when we want to describe with an arithmetic circuit our computation. So the Circom language help us here, and the compiler help us here to get these constraints in this format, and to get a way to compute or a code to compute the witness once the input is given. Okay, so there is Circom. Circom is a programming language and a compiler, and in particular is a domain-specific language created by Jordi for designing these circuits in ZK protocols. So Circom 2.0, which is what we are presenting here, has been just released. Okay, so 2 weeks ago, and it's a compiler fully written in Rust. Okay, and it provides faster compilation compared to the previous compiler, and more security, especially because it is written in Rust, but also because it applies a stronger type checking and static analysis to detect as early as possible programs that are really not intended to be correct programs in the language. Okay, so many things are detected quickly in the earlier stages of the compilation process. Okay, the aim of a Circom program is twofold, but this is part of the circuit Circom language and compiler. Is both to provide a symbolic description of the circuit, which is a list of constraints in this format, which is given in a binary file, and also to provide an efficient way to compute the witness from the inputs. okay? And this is made by providing either WebAssembly code that can be combined with JavaScript or a browser, or to provide C++ code, which is needed for large circuits. For instance, in the context of ZK rollups for layer 2, there's another project of Iden3, Iden3. So we need very large circuits that cannot be handled with WebAssembly. Okay, so this is it goes beyond the amount of memory available in the WebAssembly virtual machine. So it should be done with C++, and then we have this possibility as well. So you can choose whether you want WebAssembly or C++ or both. So Circom allows the programmer to design this arithmetic circuit at a low level, like done with electronic circuits. Okay, so this is the key property of Circom. Okay, it's like when you design circuits with Verilog. So it's just that you want to be at the level of the circuit. Okay, so it's really low level, and the key point is that all constraints have to be explicitly added by the programmer. And when we apply these simplification steps that we will talk later, we can remove signals, but we will never introduce new signals by the compilation process. So everything should be introduced by the programmer. That's the key property of the design in using Circom. So let's make a first presentation of Circom. Later on, you will see it in practice with Jose. But here we have that in Circom, the actual circuits are called components, and components are created by instantiation of a template, which is a parameterized general description of circuit. Okay, for instance, let's start with the simplest, or one of the simplest circuits we can have. So here, this is a multiplier that receives two inputs and returns the multiplication, the product of these two signals in the output. Okay, so you see here, we have this assignment here in which we say that the output is this multiplication. Okay, so the key feature of Circom is that it provides different instructions to do all these things, to work only at the symbolic level, which means we only define a constraint. For instance, here, we are just saying that in the set of constraints, we have this constraint included. Okay, but there is no computation here. We simply say this should be a constraint of describing my circuit. Okay, we can do only computations and say, for instance, use this instruction to assign the value of the output from these two signals. But in this case, we only generate an assignment, but there is no constraint associated to it. Okay, we can also write it this way. Okay, so in Circom we can do both things, and also and this is the nice thing, we can do both. Okay, so if we use this nice Circom operator, we get both. We get the constraint and the assignment, both things. It could be used in both directions, like we have seen here for the other operation. Okay, so we can do all these things, either both together or split into parts. Okay, so it would be really desirable to always use this operator. Okay, why? Because then we get both the computation level, the way to get the value of the signal from the other signals, and also to get a constraint associated to each of these assignments. Okay, but sometimes it is not possible. So let's see it in a simple example. So suppose that we want to, that also illustrates that it's not that easy to build circuits using only quadratic constraints. Okay, so let's just imagine that we want to define a circuit that checks if the input is 0 or not. Okay, so we have this, an input signal and an output signal. Okay, so then we try to think a little bit, and then, well, suppose that we our first circuit and just say, well, let's do it like this. Okay, so we put the output, we write this with this that gives you the constraint, but also the instruction. But what happens that, well, this is not allowed because, of course, this is not a quadratic constraint. Okay, so there is not the compiler will say, no, this is not a quadratic constraint. Okay, so then we say, okay, then let's forget about the constraint part. We just write it like this. But this is terrible. You don't want to write it like this because then there is no constraint at all. Okay, so you just are giving an assignment, but there is no constraint in your circuit. So if the circuit has no constraints, so what are you going to check? Okay, so we need both, and there is not that easy. So then there is a way to express it. Okay, so we do it introducing an intermediate decimal signal that express that it is the inverse of the input signal. Okay, so then you can see here that we are expressing the fact that is the inverse here as using this assignment, but also this constraint that states that after all it will be either 0 here or 0 here. If this is 0, this will be 1. Okay, which is set here. But we need this way, okay, this efficient way to express how to compute the inverse of in. Okay, note that with these two, only these two, okay, if we don't have this, okay, so suppose that we only have these two, then it would be really difficult to compute it, okay, because this is not helping us to know that this is the inverse, okay, we have nothing said about int. So we have this to express int, and these are the constraints that express that really is the inverse, okay. So if we use both, if we use these operands, like this and like this here, okay, then there is no guarantee that there is an equivalent between the symbolic part and the computational part, between the constraints and the execution, okay? So we have to be careful with this. In fact, to show that they are exactly the same, we may need even to introduce this extra constraint, okay? But, well, we may be happy with this, okay? So the important thing here is that there is no guarantee that there is an equivalence between both. That is really a desirable property, as we will see later. So another important thing in Circom is that we build circuits combining templates and creating, let's say, some components from other components like here, you see? So we have the multi-AND is built using another component, which is the E0 that we have just seen, okay? And then we also can have this notion of variables, which is an interesting new thing. It's not a signal because signals are immutable, but variables can change the value, and they are also can use to express, let's say, expressions that are built of several components. For instance, sub-expressions. For instance, here we have that sum is obtained by summing all these in that are inputs. Okay, you see? Okay, so we can compute this sum by summing all these inputs. In this case, you see that we have arrays of inputs. Okay, so we have an array of inputs, and here we are summing all these inputs. And look, what we do here, we say that the output is the result of summing all these inputs and checking if the sum minus n, which is the number of inputs we have, is exactly 0. Okay, so we send this as input to this component, and we get the output from this component. See, here we are using exactly this component to do that. Okay, so the nice thing is that the variables have two different uses. So they can be symbolic expressions. Okay, here when we create the constraints. Okay, but also they are numbers when we are computing. Okay, so look at this variable sum as these two things. So when computing the value of the signals, it is really a number. Okay, it's computing, summing all these. But when computing when generating the constraints, it is the expression which is the sum of all these signals. Okay, so it has these two meanings in the same program. Okay, depending on which part we are, whether we are in this symbolic part or in the computation part. Okay, so suppose that just to show a final example and to show the important part of this equivalence between the computation and the constraints. Suppose that we want to get from an input, we want to transform it into its binary representation. Okay, so suppose that we have this input and we want to produce this array of outputs in which this is the binary representation of the input. Okay, so of course it's clear if we were programming in a standard language, we would write something like this. Okay, in which we say that the output is obtained by extracting every single bit of the input and then storing this in the corresponding bit of the output. Okay, so that would be the standard. But this would be only computation. We need to provide also the constraints, and here we have the additional stuff to do that. Okay, so look, as before, we introduced these variables. Here, this is not that important, just for efficiency. It computes, it keeps the power of 2. And then look at this. Bsum is like, in the previous example, we are accumulating an expression which is really describing the expression that says that Bsum is the binary representation of in. So we keep this expression here, accumulating it, and finally we state it as a constraint that the input should be equivalent, okay, to the sum of the bits multiplied by the corresponding power of 2. Okay, so this would be the constraint saying that this is a representation of the input in binary style, but we are missing one property, which is that all these values in the output are binary. So this, this is what we have to add here. Okay, so this constraint here states that every value in the output array is 0 or 1. Okay. Yes. So the important thing again is that we need both, because without this, there is not a reasonable way to compute the binarization of the input. Okay. So we need, on one hand, the constraints, but also we need this to efficiently obtain the solution or the value for all the signals. Okay, so we need both. So we need both, but they must be the same. So that's the key point. So as we have said, a Circom program has two representations: the constraints and the executable code, either in WASM or in C++. So the compiler does not check whether they are related or not. Okay, so it's a programmer's responsibility to do so. So if we don't use this operand, okay, so then everything is fine. If we don't use this and only library templates, we are safe. But otherwise, we have to be sure that they are the same. And in fact, it means that both express exactly the same relation between the signals of the circuit. Okay, that is, the computed witness must be the only solution to the constraints. Okay, that's the key point. But it's a programmer's responsibility. Okay, the compiler will not check that. It's, in fact, it's not easy to prove it, and sometimes. Okay, so just to conclude this part, just taking into account that many things, I was saying, just use the library templates, because there are many things that already are provided in the Circom lib library. Okay, it has implementations for binary transformers, gates, comparators, hash functions, okay, elliptic curves, the sparse Merkle trees, and it really shows the power of the language. And you can learn how to encode complex computations using these quadratic constraints by going through the Circom lib. Okay, so now a little bit of what's different from Circom to Circom 2.0. So that's useful for those that already have been programming in Circom, and now they want to know what is anything that has changed. And the important thing, and the reason we moved to 2.0, is that we are not preserving compatibility or full compatibility with the previous version of Circom. It's not that different, but there are some difference that should be taken into account. Okay, so well, it means that if you have some projects done, you have to change a little bit something. So let's make a quick pass on these differences. And one is that semicolon is now mandatory. So you can see many circuits there that, for instance, have a line like this, in which all of a sudden, like happens with JavaScript, there is no semicolon here. So this is not allowed anymore. So you have to put all them. Otherwise, you will get a compilation error. Okay. So something a bit more maybe painful for Circom users is the fact that this keyword private public has changed completely in its use. So in fact, private and public are not used anymore in templates. Okay, so in the past it was all templates were having this private public thing, but now the only remaining keyword is public, and it's only used when defining the main component. Okay, so we cannot use either public or private in any other context, but when defining the main component. And private, in fact, is gone. You cannot use it anymore. And let's see a little bit of how it works now and why this is like this. And the point is that we have this, for instance, here, this template, and here we define the main component. Okay, and then is the point in which we say that, for instance, these two inputs are public. Okay, so we here can put the list of the input signals of this template that are public. So we can maybe take these two, or maybe we can take one. We can take no one, and then we don't need to put anything here. So we will just put main equal to a multiplier. It means that all them are private. And the default is that if we don't say that they are public, they are private. Okay. So this was what was the way to express this in the old Circom. It was like this, and this is forbidden from now on. And if you write this public private here, you get a compilation error, okay, saying that this keyword is not expected, or this token is not expected here. Okay, so we have to come back to here. And the reason is that, in fact, what happens is that all output signals, okay, of the main component are considered public and cannot be stated as private. The input signals of the main component are private if not stated otherwise, so we don't need to say anything about private signals. We just say when they are public. And the rest of signals, they are all private and cannot be made public. Okay, all the remaining signals are really intermediate signals, and they are, for that reason, they are really private. If you want to make something public, you just have to transform it into an output and pass it to the main component somehow. Okay, so you can do it, but you need to explicitly say there is a new output and then it's public from now on. But you cannot say that something in the middle is public. In fact, the semantics of the previous Circom was that they were all private if they were internal signals. So after all, the only private public thing that was important was of the template that was instantiated for the main component. Okay, so after all these private we had before, okay, they were only used in the final in the template that was instantiated to get the main component. So after all, there was a lot of private public that was never not meaning private or public, okay, because they were intermediate signals, so they were all private after all. Okay. So another difference is that in Circom 2.0, and this becomes strict because in the previous version, well, in some cases could be or not, depending on whether the signals were constant or not. You know, here this is not allowed anymore. So the circuit cannot depend on the values of the signals. Okay, so we have to think of it as a physical circuit. Okay, it makes no sense that your circuit is changing depending on the input you get. Okay, so it would be quite weird. You get a 0 in some signal, and then all of a sudden your circuit is different. Okay, so then it makes no sense in this context. So the constraint generation, which is what is describing your circuit, cannot depend on this unknown information. But there is the unknown information at compile time, which means it can never depend on signals. Okay, whatever they are, it cannot depend on signals. Okay, let's see a little bit of examples that's something you cannot do. So for instance, you cannot write an if statement, okay, with a condition using a signal and then adding a constraint there. Okay, remember that this will add a constraint saying y equal blah blah. Okay, so this is not allowed. Okay, and you will get a compilation error like this. Okay, in which you say that it cannot happen that the constraint depend on the known information. Okay, so no, not allowed. But also something like this, you may think, oh, this is why not? I would like to do that, but this is not correct either, because if this is an array of signals, which signal you are really using depends on the value of this X signal. So this would be changing the circuit depending on which is the input of X. So this is not allowed. Okay, and you will get a message like this from the compiler. So every time you get some message talking about unknown, it means that something depends on something that should be generated as a constraint depends on the value of some signal. Okay, maybe after several steps. Okay, so the compiler checks this and says no. Okay, another thing that also has changed is simply because we wanted to make it precise in the definition that all signals and components must be defined at level 0. Okay, in templates. It cannot be nested. For variables, there is no problem. You can define them at any level of nested in the blocks. But signals or components should be at level 0, at top level. Okay. So, for instance, if we have something like this, which was a part of the Circom lib for the previous Circom, that is not allowed anymore. Because here, you see, you have this component which is defined here in this nested block, and it is not allowed anymore. So how we, so you will get a message like this: signal or component declaration outside initial scope. Okay, so how do we solve this, and or how do we write this in the Circom 2.0? So we define the component at stage at first level, at 0 level, and then we create it when we want inside, and that makes it makes a little difference, because here what happens is that this component maybe is not created, depending on the value of this parameter. Okay, but it is defined there, but maybe it's not created. Okay, so this can happen and has no problem for the compiler. Okay, so another thing that is a bit painful, but not that much, is that arrays must have constant size at compile time. This is important. Okay, so many things now should happen at compile time, because we don't want things to be decided dynamically while executing. Okay, so one important thing is that it's not meaning that you need to put a constant explicitly, but here this is allowed. Okay, why? Because when we instantiate the template, we will give actual numbers, so we know that this will be of constant type at compile time, because we know that it's used like this. Okay, so we will never compile this alone. It will be together with this main component. Okay, this is also okay, because y is somehow constant as well, because we will get always this instantiated, and this y will be a constant. And if it is not modified between this and this instruction, then this is perfectly fine. What is not allowed is to use it in a function. Okay, because functions could be called in other contexts, and maybe is not necessarily be constant. This n might not be constant in some execution. Okay, so we don't want to check whether we are always calling it with a constant or not, because maybe functions are only used in the computational part, and this is not executed when compiling the code. Okay, so it's the safe thing is say no, we don't allow this. Then you will get this compilation error, and well, probably in the near future it will be allowed when if we add this some statement saying that something is constant, because then you can check that really it's only using constant information and so on, like in the sense of this const when you have C++ code or other languages. Okay, so the semantics of const as a keyword. Okay, so another thing which is not that important, but we believe it's good to ensure that we don't make mistakes and forget some part of the definition of function, is that we check for function path completeness. Okay, so all paths in the control flow should end with a return statement. Okay, so for instance, something like this would not be accepted, because here you don't have all the paths in the control flow. So you have if, else, and then there is no more else. So here it could be that there is no return in one of the cases. You may think, well, but I know that I only call this function with 0 or 1. Well, maybe yes, but we are in a context where security is important, so better to say it explicitly, that well, you don't care, or that in any other case you will return some value. Okay, so for instance, suppose that we say, yeah, return 64, well, or whatever you like. Okay, or you can do it like this way too, and in both cases you cover all paths, and then it's fine, so the compiler is not going to complain. Okay, so this is it. So there are no more important changes, okay, from the previous Circom to Circom 2.0. And from that point on, we will keep this compatibility with Circom 2.0 on. Okay, so let's talk just briefly about constraint simplification and performance before you go to the real stuff with the practical example. And here, I just want to say that when describing these cryptographic protocols, we may generate constraint systems with hundreds of millions of constraints. Okay, you can think, well, no, it's not going to be that many, but it is. It can be. And many of those constraints can usually be eliminated. Okay, so simplifying these systems is really essential for the efficiency of the next steps. For instance, this transformation to the quadratic arithmetic programs, as for instance. But also, in some cases, there are limits in the number of constraints that the ZK SNARK system can handle. And then you also need to remove unnecessary constraints. Okay, so we allow constraint simplification that do not modify the behavior of the circuit. Okay, and preserves, that's important, this R1CS representation. Remember that we will never add new signals. Okay, so we cannot say, I will simplify adding this new signal, but this allows me to remove this and that. No. We can simplify, but never adding new signals. Okay, so just a simple example. Remember this initial example with the multi-AND, and we have constraints like this. And the nice thing is that these two here, okay, so can be simplified. And this is the point. So we will replace this one by this one, okay, and we will replace, let me see, and we will replace this one by this one. And then we get, as a result, this new representation in which, you see, we are simplifying these linear constraints, okay, and we get a new system with two constraints less, but it's still in R1CS form. Okay, you see? Okay, so it's multiplication, just one multiplication here, and the rest is in the appropriate form. And here we have the multiplication of this by this, and this is linear, so we are happy with this constraint too. So the point thing is that, the key thing here is that the simplification of linear constraints is simple as it can be done just performing these linear substitutions. Okay, so what we do is every time we have a linear constraint, we expect as a substitution, a linear substitution, and we can preserve the R1CS form. Okay, so if you have a constraint like this and you apply a linear substitution, you get again a constraint in the same R1CS form. Okay, the simplification of nonlinear constraints is far more challenging, and this is work in progress. We are trying to do something there, but it's not that simple. Okay, so linear constraint simplification is very efficiently implemented in Circom. The compiler applies clustering. This was already done in the previous one, but now this is done in the same phase and just trying to avoid to minimize the number of operations we do. Okay, so we apply the clustering and prioritization as before, but in a different way. And this simplification is done using this Gauss-Jordan elimination, and we can remove all linear constraints. And every time we remove a constraint, we remove a signal. And the only restriction is that we cannot remove public signals. Okay, but this only applies to the main component. So remember. So it means that in almost all cases we will be able to remove these linear constraints. And we iterate the process because sometimes after applying the linear simplification, some nonlinear constraints become linear, and then we can simplify them again. So we iterate this process, and we are able to get reductions up to 80% of constraints, which is very important. So the only problem in this is that this is quite expensive, but it pays off for large circuits. But for instance, imagine, so you may need something like 750 gigabytes of local memory. So, well, in any even big machines, it will need swapping, and this slows down a little bit the process, but still, so we can reduce, for instance, large circuits that have at the beginning 650 million constraints to only 130 million constraints, okay? And know that now the compilation of such circuit can take more than 10 hours, okay, in a powerful machine. But the previous Circom was taking several days to do the same, okay? So this is important. And note that, for instance, in examples like this, the size of the binary file with the constraints could be about 50 gigabytes. So, and on the other side, if we think of something not that big, okay, but still big, a circuit of 10 million constraints can be compiled with full simplification with this iteration in a laptop, for instance. It takes around 8 minutes. Okay, so in my laptop. Okay, so it's something that you can do with a standard machine. Okay, so now I'm done, and it's time for Jose to give you a practical tour with Circom. Thank you.
Oh, can I just jump in real quick? I just want to make sure, Albert, that you had a quick peek over on the Q&A.
Oh, no, I couldn't.
That had a little bit to do with you. Maybe you want to just close your screen for a minute.
Okay.
Because now we're just seeing the epic
sure.
cascade of infinity. Oh, and I know someone was asking about a recording.
Should I say exit here? No.
Yeah, you just the little screen. Yes.
It. Okay, good.
Okay, so Frederico, I'm going to answer one of these because it's about recordings. We are recording this. It will be on the YouTube channel of the Zero Knowledge podcast starting tomorrow. Okay. And then we also add this on the workshop page on the website. So that was one. And then, I guess somebody deleted their questions, so maybe there aren't any more. But maybe, Albert, if you want to look through just sort of the last little bit in the chat.
But the chat, because then the question
it's true. I can see that people actually didn't, they kind of got rid of the Q&As. There were some in there, but I think they maybe had those answered already. Jose?
I've been answering several, but I don't know if all of them, but...
Well, no worries. I'm going to let you go. I don't mean to interrupt you. I just wanted to make sure that you're keeping an eye on that. Cool.
Okay. So I don't know.
Okay.
So
let me
go.
Okay. Maybe you, Albert, should answer in the chat.
Yeah.
Should I start? Yeah. Okay, so now let's move to to more practical stuff related with Circom, and I'm going to divide it in like 2 parts. In the first part, we're going to do a very simple circuit that just made some multiplication, and we will generate. we will compile the circuit, generate the witness, and then generate the proof and validate the proof. I'm going to do it quite quick because, as you see here, we have the documentation. It's just follow this tutorial. Okay, this getting started tutorial. So yeah, it is easy. I'm going to just more or less comment all the steps. Okay, the first thing is that the compiler is now written in Rust, so you need to download the Rust and then clone the repo and then just compile. Okay, but we're planning to build all the binaries for all the platforms, but this is not yet done. So the easy way, the way to go is just download and compile. Okay, so I already did this. Yeah, Docker images. Yeah, we're discussing it, but some people in the team is not very happy with Docker. So maybe just binaries, because you are just building something. So yeah. Okay. So let me, so I already compiled it. I already compiled Circom, and Circom produces like a lot of equations, and then a lot of values for all the wires of our circuit. Okay, and then from this we need to produce the proof, and then this is used by the verifier to check that the circuit that a valid input for the circuit. Okay, so the tool that goes after Circom is Snark.js. Okay, and in this case we are going to use the Groth16 system to prove that the witness, that the private input of a circuit. Okay, so let's start building a simple circuit, go through all the process, and then we will move to a more complex circuit. And essentially the idea is that you see how to think in designing a circuit and all the things that we need. Okay, so yeah, let me go here in a console, and if I do Circom, I have it. Okay, well, it's complaining because I didn't put any file, but I have it already installed. For you that used the previous version, make sure that in your path you have Circom.0. Okay, if you see here 0 something, you have the old version, you should remove it. Okay, the previous version was JavaScript, so npm remove and so on. Okay, and I also install Snark.js. You have the instructions there. Okay, so I'm just going to quickly follow the tutorial. Okay, here, so yeah, let's create a Circom 2. And then let's create our first circuit. It's a multiplier, so let's say multiplier 2. Okay, and then, well, I can copy, I think, to go faster, but I will. It is really easy, the circuit, so. Okay, so in Circom, we define circuits first. The first thing is to define a small circuit. It's like integrated circuits. So we need to define a circuit. And in this circuit is it's almost the simplest possible circuit. It's just multiplying 2 inputs. It's a small piece of a circuit. Okay. Well, in this case, it's going to be the circuit, but in a bigger circuit, this could be a small piece of the circuit. Okay. So in our case, this is going to be the circuit. So I need to instantiate this. It's create this circuit. Okay. So, and since this is like the main circuit, later we will do a more complex one. I put component main. Okay. So this is going to be the circuit, and it's a multiplier. Multiplier 2, which I have defined it before. Okay. So here I have the definition of the circuit, and then the instantiation of the circuit, and that's all what I'm going to use. Okay. The first instruction, we introduced this instruction to manage the versions, different versions, and as you see, it's just we receive 2 inputs, A and B. Okay, and then we have an output C. Okay, and then C is A plus B. So we have a computation here. And also a constraint, okay? C must be equal to A times B. And A times B is R1CS because it's just a multiplication, so this is okay, okay? This is a quadratic equation, so everything okay. Okay, the circuit, now the circuit is not important, it's just all the machinery now that to, compile and create the witness and so on, okay? Okay, so that's it. So we have now the definition of the circuit. The next thing is to compile this circuit. Okay. I'm going to do circuit multiplier 2, and I have here all these. I don't know if you see it. Yeah. I'm going to generate the equations. This is --R1CS is generate all the equations related with this circuit. Wasm is we need to generate values. You will provide me all the inputs of the circuit, and the compiler will generate a program, okay, that when we run it with the inputs, it will generate the values for all the wires, okay? So I'm saying here that please generate a program. Let's put these two together. Let's talk about the last one. The last one, sim, is symbolic, means that it will generate some debug, some information for debugging, okay? But WASM and C, these two, means generate two programs, okay, to generate the values of all the wires of the circuit. When I provide you some input, and I can provide you different inputs, and then these programs will compute all the values of these wires, okay? So let's give the run, and everything went okay. And if I do an ls now, I can see here that I have, well, I asked Circom to have all the equations. All the equations are here. Then I have some symbolic information, okay? And then it created these two files, okay? Two folders, sorry. One in C++ and another one in JavaScript, is WASM, in fact, okay? These two help us in building all the, computing all the values of all the wires of our circuit, okay? Okay, well, right now this is really easy, the circuit, so, okay. So I enter here and I see several things, but if you follow the tutorial, you just need to run, let me check. Yeah. So, yeah, and we need to create an input here, okay? So, lose the mouse here, okay. So here I'm going to create an input. Remember that our circuit just has two inputs, A and B, and will compute C. Okay, so I'm going to generate my input, okay? And it's a JSON file, okay? So now it's JSON. A was the first input of our circuit. I don't know, it's going to be 3, for example. And then B, and it's going to be 11, for example. And then our circuit, the program that we're going to run now will compute just C, which is 33. Well, this is quite easy, but if the circuit has a lot of gates, then this will be much bigger. Okay, so I have my input here, and to generate all the values of the wires of this circuit, we use this WASM program. You need to have Node.js installed, okay? And just run generate witness, okay? And for using this WASM program, and then this input, and then store the values of all the wires in this file, okay? This is what I'm saying. And okay, I have this witness.wtns. This is a binary format, okay, to efficiently store the values of all the wires of our circuit, okay, and that's it. Essentially, we finish with Circom. We need to design more complex circuits, but more or less that's it, okay. The problem, someone was asking in the chat that, I was talking with Jordi. I think they have tested this witness calculator, this WASM witness calculator, and said that was around 1 million constraints. It's okay, but if you have a bigger circuit, then it's better that you use this C++ version. Okay. Remember, this is just a program to compute the values of all the wires. Okay. And you need some dependencies. Now, in the documentation, we specify the dependencies that you need. You need three libraries. Okay, I already installed these libraries on my system. Okay, so if everything goes okay, you should just run make, and it will compile this and generate the C++ witness calculator. Okay, it seems that it's going okay. So nice. Then I have this this file here, this multiplier2. This is the program that now computes the witness, but it's in C++, so it's much faster. And to run it, just need to run it, okay? And using the input. Okay, I can copy the same input, in fact. So let me copy the input that I use from JS here. And then let's run it. It's faster. Probably you don't see a difference because the circuit is very small, but I promise that this one is faster, okay? And also generates this witness WTNS, which is the thing that we need to. Is the only the witness and the R1CS file is what we need to create the proofs. Okay, so this is the output of the Circom2.0. Okay, probably you don't trust me, so let me check that these two witnesses are the same. Okay, so I do a SHA of this, and I do a SHA of the other one, and you will see that they are the same. Okay, so if we are not wrong, if not, we have to kill Albert. But yeah, no, you're safe, Albert. So yeah, the same files, okay? But if the circuit is bigger, we recommend that you use the C++ version. Okay, so that's it. We compile a circuit. From the compilation, we obtain two ways of computing all the wires of our circuit, and this is stored in this file. And then we also have a file with the equations, which is the RC1 file. Okay. And now we are going to use another tool, which is, well, today the session is about Circom.0, but it is nice to see all the process, and then we will focus on just designing circuits. So now I need to create, I need to create proofs, okay? And we're going to create proofs with one proving system that is called Growth 16. Right now, we are starting to also integrate Plonk. It's more or less integrated, but we should optimize a lot of the process. So let's go with Growth, which is like the classical, okay? And in Growth, there is a trusted setup, okay? And this trusted setup is per circuit, okay? So each circuit has a different trusted setup, and from this trusted setup, essentially, we create some randomness, okay? And that's it. Let's go for the easiest way of doing this. Okay, so I am just to copy and paste and comment what I'm doing, but going fast, I have a problem with the cursor here. Let me check here. Okay. Okay, this one is going to create the phase one of the trusted setup. This phase is common for all the it's common for all the circuits. Okay, it's randomness that can be reused in all the circuits that you create Okay, in fact, this is just 12 is 2 to the power of 12. Jordi, I have Jordi here. Yeah, so you can with this trusted setup you can build up to 2 to the 12 two small circuits of up to 2 to the 12 constraints. Okay. Okay. So this is like the preparation, and then I can do a contribution. Since the trusted setup is a very delicate phase because typically, the trusted setup is built as a multi-party computation with several people contributes, and this gives more security because if one of the contributors does it right, then the result is okay. Okay, so with one honest contributor, that's it. That's enough. Okay, I'm not just to contribute once, but in a real system, we will have like several contributions, and also there are. I think someone in the chat is saying that there are already some information, some powers of tau available. Okay, so but here I generate this phase 1 with just one contribution. And then after this, we move to the next phase, which is specific for the circuit. Okay, so you're going to see that we are going to use now things. Well, I'm saying the chat, but you can do it as you see, Geoff. I compile the circuit first, and then I'm doing all the snark thing after. You can do it I mean, they are independent, relatively independent, until this point here. Okay, until a certain point here. Okay, so yeah, this prepare, as you see, we haven't used anything special from the circuit that I compiled yet. Okay, so we are now preparing for phase 2. Okay, this may take a little bit because, well, this is an optimization, in fact, for doing computations later faster. So these steps, you can do these steps independently of the compilation, okay? But now, then the next step, you will see that depends on the circuit. Okay. By the way, while this is finishing, just look for Circom Iden3, and it will bring you to a get started, and there you have all these steps. Okay, so my idea is to do it really quick. But it's lasting a little bit. Well, we are in 11, so I think just the last 12. Okay. This is the size of the circuit. It's 2 to the 12 equations, let's say. Okay. Let me see the Q&A while. Alpha tau. Well, let me check the chat meanwhile. About Hard Hat Circom, I was reading that they were starting to integrate it, but I don't really know how they are.
They did it, and they need to adapt to Circom 2.0.
They need to adapt some things, yeah. By the way, you can talk, because if you want to talk, I mean. Okay, it finished. And now the specific part, okay? So as you see here, we are using multiplier R1CS. These are all these constraints, okay? All these equations that are forcing that the inputs and the outputs are related correctly. Okay, so yeah. Now this is generating some stuff, which is the ZK. This is all the previous cryptographic material merged with the with these equations, and we create here all the cryptographic material for the prover and the verifier. Okay, and now we can contribute, because we still need to generate the randomness of this second phase, which is specific for the circuit. Okay, so yeah, we created the file that will contain this, but in this, okay, as you see, is entropy. Okay, so now here, this key already contains the randomness. Okay, And as I said, is valid for the two, for the prover and the verifier, okay? Now let's extract the part of the verifier, okay? With this command, I'm storing here in the verification key JSON, I'm extracting the randomness and the stuff that the verifier needs, okay? From this key. Okay. And now we have all the randomness and all the parameters necessary. Then now we have two processes. One guy, the prover, is going to generate the proof, and another guy we will provide the proof to this other guy or girl in this case, and the other one will check that the proof is correct. Okay, so let's do this. Okay, so this is the first part, generating the proof. Okay, to generate the proof, as you see, we use the witness. I mean, I need to generate. I'm the prover, so I need to provide you information. I mean, I need to provide you this multiplier. This ZK contains all the randomness, okay, to generate the proof. The witness contains all the values of the circuit, and with these two data, we generate the proof and some public inputs and outputs. Okay, that the proof will need some values here, and then we also need all the public things here. Okay, so this command will generate this proof and public. Okay. Oh, something. Well, we need the witness here. As you see, we were using the witness. So let's copy the witness from any of the witness witness programs. JSON. Let me check. It's the name multiplier. Maybe okay. Copy multiplier to this one. It's okay. So the witness. I copy the witness here. Okay, and then again, okay. So now we have the proof and the public inputs and outputs. Okay, so I just need now to verify the proof. Okay, we can verify the proof in several ways with just a separate program. Okay, and I'm going to do this, but the Snark.js also can generate a smart contract that also proves, also checks these proofs. Okay, so let me do just the separate. Using Snark.js, you can prove. Okay, so to verify, I just need to pass the cryptographic stuff for the verifier, which is inside the verification key, the public inputs and outputs, and the proof. Okay, and well, you must trust that it checked everything. Okay, so yeah, this is okay. Okay, if I try to manipulate something, I change the. Let me check. It's 33, so let's change to 34, for example. If I try to verify, it will say that it is an invalid proof. Okay. Well, this is the whole process, and you can go through the documentation, and it's the same. Okay. So, but now we are more interested in designing circuits. Okay. So this is a multiplier. It's okay. You can prove in zero knowledge that you know two numbers, but it's not very exciting. So let's try to do something nicer. Okay. And I must apologize. I don't have like the nice slides that Albert has, but I'm going to draw it like in a blackboard. Okay. So let's try to design a step of a voting protocol, there is a step in which we check that someone belongs to a census. Okay, so we have a watch. 1 minute. Sorry. 1 minute. Oh, it should be this one. Let me check. Oh, yeah, now it's working. Okay. So let's do this. Okay. So there is a step in the protocol that I need to check that someone, okay, is in a census. Okay. And someone is going to be a public key. Okay, the identity of someone is going to be a public key, and the census right now is something known. Okay, so let's say we have 4 public keys. Okay, so public key 2, public key 3, and public key 4. Okay, so I would like to check that this public key is one of these 4 public keys. Okay, but not only this, I want to check that you really own this public key. So in some way, you need to use your secret key. Okay, so it is very obvious. You could say, okay, provide me something signed, provide me a signature. Okay, provide me a signature of something using your secret key. Okay, well, this is very dangerous. Providing a signature of something, what? Something that you give me. I mean, when you sign something, you must be very precise. So your signature cannot be used in other contexts. Okay, so we are going to sign something very specific. That is, okay, I want to vote for mayoral elections in Barcelona to 2021. Okay, so I'm signing here something very precise. Okay, and I'm using my secret key to, to sign this. Okay, we're going to call this the voting ID. Okay, it's an identifier of the voting that I want to do. Okay, and I can provide this signature to someone. It's okay, and you know that the verification will just use this signature, and well, the possibility and the verification algorithm uses some public key. So we can try all these 4 public keys until one of them, to check if one of them is okay. And yeah, you are in the census. Okay, nice, but not zero knowledge at all, obviously. Okay, so when I do this, I mean, so someone is going to check this and say, okay, is this okay? This signature has been done with this public key. Okay. But then this is identifying me. So we want to do this in zero knowledge. Okay. So to do this in zero knowledge, we can try to build a circuit. Remember that we are with Circom, we're building circuits. Okay, and we have several inputs. Some of these inputs, some of them can be public. Okay, and someone might be private, which is by default. By default, all of them are private, but you can also have public. And then we have the output, okay, or outputs. And typically outputs, outputs are public, okay. Okay, so I want you to give you a proof, okay, that I know a secret key from one public key of the list. Okay, so I want to prove you this. Okay, so, and I'm going to build a circuit to prove you this. Okay, so let's go for our first version of the circuit. By the way, you probably know that several public key schemes. Okay. You know that we have like several ways of building pairs of secret keys and public keys, okay? We have elliptic curves, or you can use multiplicative groups, or several different ways, okay? But with zero knowledge, we can also use a hash function to build a pair of public keys. And I'm going to do this in the first moment, okay? So I can use a circuit in which I implement a hash function, okay? Some hash functions with Circom, we have like several implementations of hash functions. we have, for example, the implementation of SHA-256. Okay, but the problem is that SHA-256 was created. Well, it makes a lot of binary operations. Someone was asking, the wires in our circuit can be zeros and ones. Yes, can be zeros and ones, but then you are losing a lot of power. You are using just the wire for 2 values, okay? But you can do it. And SHA-256 was created with binary operations, and which is translated means that you need a lot of equations, to express this function, okay? So there are nicer functions like Poseidon, and Poseidon is also implemented in a library of circuits that we are providing together with Circom, okay, which is called CircomLib. Okay, so in CircomLib we have Poseidon too. So we could build this circuit, okay, and use this public key. Use the output of this circuit as a public key and the input of the circuit as the secret key. Okay, so if I can prove you that I know the secret key associated with the output of a hash function, well, this can be public. So this is a scheme of public key. This can be public, and since I'm proving in zero knowledge, you will not know anything about the secret key. Okay, so yeah, this is okay. But in fact, what I want to prove is that I know the secret key with a list, which is the secret key of this secret key produces one output that is one of a list. Okay, let's try to build this circuit. Okay, so it should be something like this. Okay, it's a secret key. I have my secret key. I put the secret key in a circuit. Okay. And then we do the hash inside the circuit, okay? And this produces my public key, okay? And then we should check that this public key is one of the 4 possible public keys, okay? Public key 1, public key 2, and public key 3 or 4. Okay? How do I do this? Well, I just take this wire and connect to an is equal, around, it's okay. Is equal, okay, and I provide here the public key 1, okay. If these 2 are equal, then the output of this part of the circuit will output 1. If not, it will output 0, okay, so 1 or 0. And I do the same for I take this signal here and the public key 2 and so on, okay. And then I get like different outputs. And then I do the OR here, okay? So if any of this is 1, then this outputs 1, okay? This is the output, and this output is going to be public too, okay? So in this circuit, I have the secret key, which is an input, and it is secret, okay? And then the circuit will check. It will check without revealing anything about this input, that this secret key, after doing a hash, produces some output that is equal to one of these 4 public keys, okay? 3 and 4, okay? These secret keys, these public keys, sorry, they are also public, okay? So they are also inputs of the circuit. Maybe I should draw them, okay, outside. So this is a circuit in which I'm providing 5 inputs, okay? The secret key, which is private, 4 public keys, okay, which are public, okay? I said that secret is private input, okay? I provide 4 public keys, which are public, and then the output, which is also public, okay? Well, this could be a simple circuit that we could build, okay? But it is not okay. This circuit has a problem. The problem is that if we have a real census of a country, for example, then we should put here millions of public keys. So it is not a good idea. There is a better way to do this, okay? Which are our friends Merkle trees, okay? So let's go to build a Merkle tree to build this circuit. Okay. And let's start with a Merkle tree of just 8 nodes. Okay. So what I'm going to do here, I'm going to build a Merkle. The idea is to create a circuit that validates that one of the inputs belongs to the Merkle tree. Okay. So let's create a Merkle tree. Okay, with 8 values. For example, I'm going to create a small one so I can make a picture of it. Each of the leaves of the Merkle tree, they're going to be public keys. Okay, so I need to do here a hash, okay, of secret key. I mean, all the keys here will be hashes of secret keys. Okay. Okay. And then we build a classical Merkle tree, which is we take these 2 values, concatenate them, and make a hash. Take these 2, concatenate it, and make a hash. Let's put some. Let's do this and this. Okay, this is the root. We're going to call this the first level, then the second level, and then the third level. Okay, so this is a Merkle tree that has 3 levels and 8 leaves. Okay. Remember that we're going to name this one as H000. Okay, this is going to be H001. So this one here is going to be H00 and is simply the hash of 000 concatenated with 001. Okay. Well, I'm going to just put without H. I will put just the numbers. Okay. So this is going to be 0, 1, 0, 0, 1, 1. Here is 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. So in the first level, we will have H0, which is the concatenation, and here we have H1 and the root. Okay. So this is the structure that we're going to use. And then you want to prove that you know some secret key of this. Then you want to prove that you own some secret key of this tree. For example, this one. Okay. So I want to prove you that I know the secret key, which is, in this case, is a preimage of a hash function. Okay. Then to make this, if you want to prove me this, then is regular Merkle trees. So I know the secret key, so I can do the hash and compute this thing here. And then I need to provide you some siblings, some nodes of the tree that will prove you, that will prove anybody, in fact, that I know the secret key. Okay, I need to provide this node here, so you can do the concatenation and hash and obtain this node here, and then concatenate with this, apply a hash function, obtain this one, and then with this other sibling, you can obtain the root. Okay, these in blue are the siblings, or also all the siblings together are the Merkle proof. And essentially, we check that with the siblings, if you do all the hashes, you end in the root. Okay. And if you provide me all these nodes, I will be convinced that this node here is in the tree. Okay. Okay. So yeah, let's try to build a circuit with this. Okay, there's something. We will go back to this picture. Okay, in a moment. Maybe you could think, okay, then I want to prove you that I know a secret key that is in the tree. Okay, so maybe you could think, okay, try to build a circuit like this. Okay, well, it's not a nice. Well, this is better. And I input here the secret key. Okay, I input here the siblings, an array of siblings. And then this circuit should do all the hashing and all the stuff and output here the root. Okay, maybe the question is, what is public here? What is private? I don't know if someone want to, obviously the root of the tree seems that needs to be public. Okay, the secret key obviously seems to be private. Okay, I should not reveal my secret key. Regarding the siblings, what do you think? Should be public? Should be private? I don't know if someone wants to ask, but should be private. Okay. If I mean, to check, as you said before, we need to provide the public signals to the verifier. So if I provide the siblings, he will know where I am. Okay. Yeah, the nullifier is going to appear in a while. Okay. So yeah, this is enough. I mean, to build my circuit. This is not. I mean, there are enough entries here to build my circuit, and the answer is no. Okay, because I need to. I need to provide a circuit that allows you to prove any of the possible secret keys. Okay, and see that if we have this secret key, then we need to hash. I mean, if I provide you this secret key, then I need to hash this secret key using it in the left, and then hash with this sibling on the right. Okay, and then obtain this. And in this hash, I need to use the value that I just computed. I need to put it on the left and this on the right. So, I mean, and you know that the hash of A concatenated with B is obviously different from B concatenated with A. So, in some way, I need something. I need to add something to the inputs so I know in which order do I need to do the hashing. Okay, and for this reason, we are going to use the key. Okay, so this node here will have the key 000. This node here will have the key 001. This node here will have the key 010, and so on. Okay, and the key of an element will tell us which is the order in which we have to do the hashing. Okay. For example, for this example here, for example, okay, 011 means that the first 0 means that in the first hash, the last level is the last bit. Okay. So in the last level, I need to put this node on the right. Okay. In the next level, also on the right. Okay. But in this level, this hash goes on the left. Okay. So this key will tell us which is the order in which we have to do the hashing. Okay. And this is something that we need to include in the circuit to do the correct hashes in the correct order. So here we need also to include a key. Okay. And obviously this key is also secret, because if not, you are telling in which position you are in the tree, and then we know where are you. Okay. Okay. So if I make a proof to you and give this proof to you, okay, in which only the Merkle tree, only the root of the Merkle tree is a public output. Okay, only the root is a public input, and then I provide you all the stuff to prove. Well, all the rest of the things that create the proof. Then I will prove you that I am in the tree. Okay, but you don't know in which leaf of the tree I am proving, which means which secret key do I know. Okay, so well, this also creates a problem, because zero knowledge proofs, you can generate as many zero knowledge proofs as you want. Okay, and all of them are different. Okay, in this case, proving that I know a secret key of the tree, as someone said in the chat, if we are not careful, this means that you can create like 2 different proofs, but you are proving the same secret key, okay? So we should not allow this, okay? And, well, in this case, we introduce another thing here, which is remember that we started with, I want to vote for mayoral election in Barcelona. We're going to introduce this also as a public input here. We're going to call this the voting ID. Okay, and essentially we're going to do, the trick is to do a hash between the key, the secret key, and the voting ID to generate something, okay, that is related with the elections and with my secret key, and is something that is another output of the circuit, okay, and is the famous nullifier. Okay, if you try to do another, I mean, each time you try to do a proof with the same secret key, it will yield the same nullifier. So essentially, you cannot try to be two different persons. Okay, this is the idea. So, well, in fact, this is like part of a voting scheme. Okay, so let's focus just right now. Let's focus on trying to build this part here. Okay, let's try to focus on building the verification of a Merkle proof. Okay, so let's try to see how to build this thing on Circom, and it's not as easy as just a multiplication, obviously. Okay, so to build this thing here, we will need. Let's go here. Maybe I'm running out a little bit of time. Now I see it. I should go a little bit faster. Okay. You need to build some. I mean, you need some help in some way. The circuit is just going to verify. I mean, you need to provide to the circuit the root. You need to provide the circuit all the siblings and all this stuff. Okay, so probably you're going to need some external programs. Okay, to build this. I mean, to create this information. Okay. I mean, probably if you are in an election, you will be given like several public keys. Okay. Okay, I will be given an array of public keys. Okay, but from this I need to compute the root. Okay, so and what else? Then I need to compute the siblings. Okay, because I need to provide the siblings to the circuit. So I need to compile this. I need to get the siblings and all this information, all this stuff. To build all this stuff, I need a hash function. So I need to do hashes. Okay. We are going to do not SHA-256. We are going to do Poseidon hashes because they create less constraints on the circuit. Okay. So what I'm saying here is that I need some external things that are not in the circuit. The circuit is going to verify that. That you know a secret key, okay? But to build all this stuff, okay? Well, we provide, for example, the Poseidon implementation. We have a Poseidon implementation made in JavaScript, okay? So, finally, to build this circuit, we are going to use some pieces that we already created, okay? We are going to use templates from Circom. Okay, so this is one of the main pieces. You have a library of already created small circuits that you can integrate in your circuit. Okay, so this is one of the things. On the other way, you will on the other hand, you will need some external programs to manage, do hashes or manage all this stuff, okay? We provide some programs, JavaScript programs in Circom.js, okay? You also have available this other package, okay? Okay. So let's try to build this stuff here. To create this Merkle tree and so on, I'm going to copy and paste quite fast a little bit of code, okay, that just does this, okay? Just let me explain you what it will do, and then I copy paste, okay? So we are going to use a function which is called Merkleize. We are not going to analyze it. Merkleize. And for this function, I'm going to provide the field because I'm going to do hashes, but I'm going to do hash of elements. Remember, all the wires in our circuit are elements of FP, which means are elements that go from 0 to P minus 1. Okay, so really we can have here from 0 to a really huge number. Okay, P is a very big number. Okay, so and we need to do operations in this field. So we provide this F field. Okay, by the way, this is implemented, if I'm not wrong, this is implemented in FF JavaScript or JavaScript FF. FF JavaScript. Okay. This is another package, okay? So here you are seeing all the pieces that surrounds Circom. It's not only Circom, okay? There are several. It's inside Snap.js. Okay, it's also in the Circom.js, okay? You will see it later because I'm going to take a look at this. Okay, what else needs this function? Obviously, this array, okay? And this array, I'm going to call it, let me check. I need a hash function, by the way. I need the implementation of the Poseidon in this case. Okay, so I'm going to pass this function, the hash, the array, okay, and the number of levels. Okay, in this case, it's going to be 3, okay? And this function essentially will create an array, okay, with a big array, okay? It will put all the public keys in the tail of this array and then take 2 of them, create a hash, 2 of them create a hash, 2 of them create a hash, and create another level here. Okay, this is going to be level 3. And then it will create all the hashes of level 2, which are half of them. And then, well, it is not at scale. There are 2 only at level 1. And then it will put the root here. Okay, this is the Merkleize function, and you need a little bit of external program to do this. Okay, the circuit just needs some signals and do the verification. Okay, so let me create it. Okay, so finally, if maybe we cannot finish it complete, or maybe we can provide you a repository with all the software and so on, and just try to you can maybe finish it. Okay, so now I'm going to create mkdir, let's say census check. Okay, this is. And as I said, we not only need the Circom stuff, we also need some JavaScript stuff. We will need some Circom stuff. Okay, so let's create these 2 directories. And inside JS, let's create this. Merkle tree to JS, and this is a helper. Okay, to build all the necessary things that we need to create proofs for our circuit. Okay, so let's edit this. I'm going to really copy paste all the functions. Okay, I'm not going to discuss them in detail. I was a little bit optimistic with the time, but okay, this is the Merkelize function. Okay, it's a recursive function. All the recursive functions have like the same structure. Check if we are in the last case. Okay, if not, do whatever I need to do on my level, and then call again the function, and then with the return, build the final return. Okay, but sorry, but I'm not going to discuss it. By the way, I think I can copy, in fact, all the file. Let me.
Jose,
yeah.
you have another 10 minutes at least on our clock. I hope that's enough time.
No, it's not going to be enough time.
Also remember that what we're just going to do is we're going to break to start the puzzle, but you can actually continue that after. So
I think because I would like to discuss a little bit the circuit.
Okay.
So
sounds good.
Yeah.
Cool.
Maybe. Well, I continue for 10 minutes and then okay.
We do a little break where we announce the new puzzle, and then you're welcome to continue.
Just point to the repo and that's it.
Yeah, I'm going to
Go directly to the circuit.
I'm going to go directly to a circuit. Yes, this is nicer. Okay, let's go directly for the circuit, and then I will provide you we will provide you a repo, okay, with all the information. So yeah, then let's see how the circuit for verifying. Let's focus on Circom then, and all the related stuff we will provide you. Let me check what I did. One minute. Okay. So, and this is going to be important because it's the strategy to build a circuit. Okay. So, if I take a look at, maybe I can copy this Merkle tree. Okay. So, I'm going to build something, okay, to check one of the levels of the tree, okay? Remember, I'm going to provide what we have on the which is the input of our circuit, okay? Remember, it is going to be the key, okay? Well, let me draw it with a key. Okay, but the key is going to be a number. So I need to convert this key. Okay, we will have a circuit here, which is num to bits. As its name says, it converts one number to the corresponding bits. Okay, so in the circuit, I will provide, I don't know, the number 4, 5, 8, whatever. Okay, and this will convert this in 3 bits in this case. Okay. And here I will have the key. Okay. In this case, for example, if I'm trying to prove this one here, this is 3, right? So I will provide a 3 as a number, and the output of this circuit is going to be 0, 1, 1. Okay. And I'm going to use this 0. Well, I'm going to use these numbers. Okay. To know the order in which I need to do the hashes. Okay. This is the reason for why I'm using the key as an input in the circuit. Okay, and then I need to do. Let me focus on this on one of these nodes here. For example, let me see what happens in this check here, okay? So on one level, okay? Let's call this generically level I, okay? I'm going to build a template that it will verify one level, okay? And I am going to instantiate this template several times, as many as levels, okay? And this is the reason for we are using the for loops and so on, these things to create the circuit. The specific parts of the circuit need to be instantiated, okay, and need to be known, as Albert said, okay. So let's create this stuff here, okay. So I'm going to call it, okay. I'm going to call this. Later we will provide you all the circuits and all the stuff. Okay, this is going to be a Merkle tree of 2 binary Merkle tree. Okay, verifier level. Okay, so I'm going to create one template that is it's a small piece that verifies a level. Okay, to verify a level, this is going to be level I. To verify a level, what do I need? Okay, I need to do the hash of this level. Okay, so what I need something. For example, in this level, this node here is computed from the lower level. Okay, I'm going to call this low. This is an input of this template. Okay, and this comes from another MK to verifier level. Okay, then I will connect if I am in this level, okay, and I am checking this key here 001, in the second level is a 1. Okay, you see in this level, the value of the key in this bit is going to tell me how to do the hash. Okay, so I will take this one here and I call it selector. Okay, and this inside this circuit we will have a selector circuit here that essentially it will just outputs like the input and the output. It either copies the input to the output and the input 1 in the output 1, or it is better to say left and right. Okay, input left and input right to the output left and output right. Okay, right and left, or if this circuit has another input, which is selector, that if selector is 0, doesn't cross anything, but if selector is 1, it will connect like this. Okay, it will connect right to left and left to right, and then we hash. Essentially, inside, we're using this selector to change input and output and do the correct the hash in the correct order. Okay, and the bit of the key is who is telling me is the input to this selector and decides if we need to cross or not cross. Okay, so I'm going to put the selector here, and then I need to do the hash with the sibling, in this case with this sibling here. So I need to input the sibling here also. Okay, and the sibling we're going to take, remember that we provide the siblings as an input, okay, and they were secret. So I'm going to take sibling I and connect it here. Okay, the sibling of the, I'm going to take the array of siblings and select sibling I and connect it here. Okay, and then this will do the hash and produce a new value, which is root, or maybe it's better to say to root. Okay, it will produce this value here. Okay, so this is the pieces that we are building here. Okay, and essentially we just need well, this MK2 verifier level. Okay, we need this selector we need some hash function to do the hash, and then connect all this. I mean, then I have like all these pieces, and I need to put it in a motherboard and put all these pieces and connect everything. Okay. Well, Circom allows to do this. Okay. Let's see the code. Okay, of Circom. Or maybe we can do I'm going to show the circuit and a little bit of testing, but we want to just take a look. And then I think that the best idea is to provide all the people the link, okay, so they can check out, try stuff, I don't know, ask questions. They are very welcome to join the Iden3 Telegram group, and we are answering questions there. So
nice.
Yeah.
Would it make sense to share the link now, or you only want to do that?
Yeah.
Yeah.
The link of the repo of this, yeah, it makes sense. Let me check.
Cool.
1 minute. By the way. A little trick, but is this? Maybe I can cut and paste it here. It is not finished. Okay, but anyway, I paste it here, and it has like all the code. Okay,
that's awesome. Okay.
Probably I'm going to convert this in a more in a tutorial and write down everything and so on. So when it's available, I can also provide.
Perfect. And actually, we can put that on our like workshop page after the fact, because we're putting the videos and slides on the workshop page now. So if you want to share that as well, I think that would be awesome. Okay, take it away.
Okay, so let me. Share and let's go to just take a look at the circuit. Okay, in circuits. Okay, you will see. Well, tester no. Circom. Yeah, this is the circuit. Okay. So as I said, we need the switcher. Okay, remember that the switcher is something that selects, I mean, leaves the input and output not crossed or crosses, depending on the selector. Okay, then I need the Poseidon, which is the hash function, and in this other file we have the number 2 bits. Okay, that we need to do the hash in the correct order. Let me check that I don't see you. Okay, now. So here we can see how we implement the Merkle tree verifier level. Okay, remember that it has a sibling. The sibling is the value which I need to hash. Low, this is the value that comes from the lower level. Okay, selector will come from converting the key to bits. Okay. And then the root, which is the hash, okay, of that this piece is performing, okay. So and then we instantiate, as Albert was saying, we create a switcher here. How I instantiate a switcher from the Circom lib, okay. So just need to include here and then just create the instantiation. Then I create the hash, okay. And then I connect the selector, and maybe I can help with the picture. Remember that the selector, well, I didn't draw it like very well, but here the selector, well, in fact, it's called switcher. I instantiate a switcher, and then I connect. In this switcher, I connect the low and the sibling I. Okay, I connect these two, and these two are what I need to hash. Okay, so I'm hashing one level. Okay, and this comes from sibling I and the low and the low signal. So in the switcher, I need to connect, and the switcher inside has two signals. Okay, if we take a look at, yeah, it's not going to be here because it's in the Circom lib. I don't think I have it. 1 minute. I am going to do npm install Circom lib. All the circuits are also an npm package. If you download this, if you clone this repo, it has a package JSON with all the of the JavaScript packages. Okay, I didn't install them, so let's. Okay, so now I have these node modules here, and inside we should have Circom. Check. Iden3 Circom lib. Okay, we can go Circom lib. We can go to circuits, and then we can take a look at the switcher, for example. Okay, this switcher, as you see, is just taken left. The inputs are a selector, left and right. I think that if selector is 0, it will not change these two values. If selector is 1, it will change them. If you see here, these equations is what are saying. Okay, so if selector is 0, then aux is 0, which means that output left is left because aux is 0. Okay, if selector is 1, then we have left minus right. So output here is right minus left, so minus left, so it's right. Okay, so output left is right, and if you do the same, if you plug here this, output left will be left. Okay, so it's switching it's computing and verifying that we are switching the values. Okay, so these are the we are computing the value of output L and also forcing that the output should fulfill these equations. Okay? Computing and forcing that these equations are fulfilled. Okay. So in our example, we need to connect the left and the right to the sibling and to the low. Okay. We need to this value key here comes from the low and the sibling. Okay, so we will see this in the circuit. Okay, so if we take a look at the circuit, where is it? But building circuits with Circom mainly is most of the time maybe connecting already done circuits in the Circom lib. Okay, so this Merkle-True verifier is like this. Okay, so the selector that is an input of this bigger circuit, the MK, this verifier level, it receives the sibling and the low and the selector and the root. Okay, it produces the root. Sorry, but it receives these three. Okay, I connect the sibling to the right input of the switcher, and I connect the low to the left input of the switcher, and then the selector to the selector on the switcher. Okay, and this will produce the switcher. Remember that produces two outputs. Okay, which are switcher out L left and switcher out right. Okay, so now I use the Poseidon to do the hash. Okay, I connect the hash. Okay, I connect the hash function with the left, with the switcher left, and the other input of the hash function. This Poseidon is of two values to the output right, which will be in the correct order according to the key. Okay. And I then I connect the output of this hash, which is the hash value, okay, to the root, which is the output of this box. Okay, so as you see, building circuits is just it's a nice idea to make a picture, okay, and see what you need to connect. Okay, it's just this picture, maybe not so nice, but I promise I will do some pictures and provide you some some link with a nicer pictures. Okay, and now. Someone was asking, and I don't understand the difference between, this double and the for and the ifs and all this stuff. Okay, well, this is just, I mean, the loops, the ifs, all these constructions are to create the final circuit. Okay, in our case, we are going to create a circuit. Okay. And the circuit is going to be a concatenation of these Merkle-2 verifier levels. Okay, so if I have 3 levels, I will create a verifier, not from a level, but to verify everything. Okay, and I will provide 3 levels in this case. Okay, and this is like the final circuit. So it is receiving the key. Okay, the value, which is the secret key in our case, the root, which is the final root, the root of the last level, and an array of siblings. Okay. And now what I need to do? Well, I need to instantiate this component. Okay, number 2 bits. Okay, with 3. So this is a box that converts any number to 3 bits. Okay, so keys should be between 2 and 3, okay, but if you provide something bigger, well, it will convert this to 3 bits. So you can use bigger keys if you want, but it will take only the least significant bits. And then I create an array. These levels will contain boxes like this, okay, verifier levels. Okay, so this is a component built with three levels. Okay. Later, I will assign each of these. Okay, to this variable. Then I need to do. This is a technical, minor thing, but remember that I need to do. I will provide the secret key. Remember. And I need to do a hash of this secret key. The first thing that I do is this. And then we need to do pairs of hashes, okay? Because you are now in the tree. But I need to do like a first hash, okay? So this is easy when you take a look, if you understood what we are building. So I'm instantiating here a Poseidon of just 1 value. So this is to do a hash of 1 value, okay? This is the hash of the secret key, okay? We are going to use this to create the hash of the secret key. And then we connect the value, remember that this is our secret key, to the input of this hash, okay? And, well, this is going to be the first low value, okay? Then we connect the key that we are receiving externally, okay? We connect it to the number 2 bits in template that we instantiate here, okay, and to the input of this template, okay. So I'm connecting, it's a little bit, okay. So is this part here, okay, the num2 bits. I'm connecting the key to this element here, and this element here is in, okay, the input. So I'm connecting the circuit is receiving a key. And then I'm instantiating a num2 bits, and inside this is called in. So I'm connecting things. I'm doing this wire here. Okay. So this is the connection here, and then there's a for loop. Okay. And what is creating is like it putting all the. I mean, it's building the circuit. It's putting all the integrated circuits. We created this verifier level. And well, essentially, we are creating the circuit for the current level, and then connecting the sibling of this verifier to the siblings I. I mean, this is from the output. This is from the inputs of the circuit. I'm connecting this. I'm connecting the selector, okay, as I said, to the correct bit of the num2 bits output, okay? And then if we are in the first level, okay, we just need to, I mean, if we are in the first level, then the value that I need to hash comes from hashing the value, okay, hashing the secret key, what I said. So this is levels I low, okay, well, I'm connecting this to the hash. If not, well, I am connecting the low, I mean, the root. I'm doing this in the reverse order, as you see, okay? So I'm connecting from up to down. So I'm connecting the level +1 root to the low of the current level, okay? And finally, the last, the level 0 is the final root, okay? Well, that's it. I think I have a nicer picture. Again, well, again, it's the same picture. Let me see in the README. Okay, here. So it's just doing this, okay? Level I and connecting siblings I and connecting the root here to the low here, and the selector comes from this, and then it outputs a root, okay? And the for loop is just building this circuit, okay? Just connecting more, connecting circuits, verifier level circuits, small templates, okay? We're going a little bit fast here, but hopefully you will take a look and will see that it's just connecting, and the for loop defines how to connect all these templates, okay? All this definition of small pieces, and to finally build the big circuit, okay? Finally, when we have like everything built, then we instantiate. We just create another file in which, well, in fact, we're going to test this. So in the test circuit directory, I create like a tester, which is just an instantiation of the definitions that I make. Okay, I'm going to create a Merkle-2 verifier for 3 levels. Okay. Now you should install Circom tester. Okay, what is Circom tester? It's another tool of the ecosystem. Circom tester will do all the things that I did manually. To create, I mean, I compile the circuit manually, and then I run the witness, the program calculating the witness. Okay, I do all this manually, but when you want to do a test, this is a helper, okay, JavaScript helper to do all this stuff. Compile the circuit, run the Wasm or C++, well, I don't know if Albert can take a look at Joff, but all this stuff is already implemented in the Circom tester to create tests with JavaScript. So just need to do npm install Circom tester. Okay, you will see it on the package.json of the project that we are providing. Okay, and then we just built a test. Okay, so how we do the test? Okay. I need, in this case, the Wasm tester is just that I'm going to compile the circuit and create and just create the Wasm the Wasm wire calculator, okay, or witness calculator, the program that computes the wires. Okay, I'm going to use the Wasm version. Okay, then the Poseidon is implemented in Circom lib.js. Remember, Circom lib.js are all these helpers built in JavaScript, okay, that are outside circuits, but you need them, okay, to provide inputs to the circuit or check things, okay. Then if I had more time, but Merkelize and get Merkle proof, this is implemented in this function. Is just create the Merkle tree and compute this array that I mentioned at the beginning with all the values. Okay, and get Merkle proof. It will just get the siblings. This is to get the siblings, and so we can plug them on the circuit. Okay. And the field, well, all the elements that we are using are on the field F in this case. So to make this test, we just call this wasm tester, providing the path to the file that I just created, instantiating. Okay, I instantiate what the circuit that I did. Okay, so I just call this, and this will compile the circuit as I did manually, and go then and generate also the all the wires, okay, which are stored here in the circuit. Okay. Well, then to do a test, okay, I just need to call Merkelize. Will generate all these. Will generate this vector that I said with all the values. At the beginning we have the root, then the hash values of the first level, then the values of the second level, and so on. So here I am making a Merkle tree with these 8 values. Okay. So in this M is just an array with all the hashes. Okay. In the position 0 we have the root. Okay. So then I call this function. If you take a look, you will see that it provides you an array with all the siblings. Okay. And then I call my circuit. Okay. And remember, which were the inputs of our circuit? The key. Okay. To do the hashes in the right order. The value, which is in our example is our secret key, and then the root, okay, which I've computed here, and the siblings. And then I have this function here, okay, and then I execute calculate witness. Okay, right now I'm executing the wasm program that I executed manually on the console. I am executing this from this Circom tester. Okay, and essentially this test, if everything goes okay, this doesn't throw any exception. If something goes wrong, then you will have the test will fail. Okay, and more or less that's it. I mean, yeah. To recap a little bit, I mean the ecosystem of tools that we have. Remember, we have Circom. We have Circom lib, in which we have already a lot of templates, a lot of small circuits. Circom essentially is a language to connect all these templates, essentially. Okay. Then you need external things to provide the correct inputs and outputs. Okay. And for this, we have Circom lib.js. Okay. And then you need, if you want to do automated test, you cannot do this compilation manually. And we provide just Circom tester, which is also a JavaScript package. So you can, you can execute, I mean, you can compile the circuit and then run the witness, the program that computes the witness and see if there is any problem and so on. Okay. Maybe we will complete this test a little bit more with, you can also check signals and so on. So, yeah, what else? Just a small thing that I didn't say, but while we are compiling, we can see the values of certain wires. Okay, just in Circom, you can do log. Okay. Okay. Someone is asking if there will be Circom lib rs. Well, maybe in the future, not right now. But yeah, all these programs that allow in Rust, I mean, yeah, you can build this in any language that you like. Probably not in a. We don't have it right now. Okay, but well, I hope that I described more or less all the tools. I know that finally I have to accelerate a little bit. Maybe the best thing is to take a look at this, check, and then if you have questions, maybe I really advise you to you can add to the Iden3 Telegram group. Okay, we are very friendly there. So I don't know, Albert, you want to say something else?
Not really. So
Not really. Okay. Well, I think that's it. As I said, I will try to write this down and maybe publish in the next few days. And well, it was a pleasure, and I hope you have a good time with Zero Knowledge, which is really fascinating.
yeah, thank you all
Thank you all.
for being here with us.
Bye-bye.
Bye-bye.
Thanks, Jose. Thanks, Albert. Thanks, everyone, for coming.
Thank you so much, Anna.
And
Thank
just
you so
again,
much.
we're going to put this up on YouTube. So if you missed anything, and now you have actually the document to be able to go through it yourself. So this is pretty cool. Okay.
Okay. Thank you. See you soon.
And see you next week, everyone, for the software one.
Bye-bye.
Bye.
Bye.